Welcome to number series seminar. Today we are glad to have Hang Xue from University of Arizona, and he's going to tell us about the local Gan-Gross-Prasad conjectures for real unitary groups.
Well, thank you very much for the invitation. Well, I should say that I like Princeton very much. I really want to visit back to Princeton in person. And I spent 1 year as a postdoc at IAS. That was perhaps the best year that I've ever had. And well, I was very productive, and the life is really enjoyable in Princeton. Well, I really miss the dining place at IAS. It's basically nothing but perfect. I like it so much. So I'm going to talk today about this local Gan-Gross-Prasad conjecture for real unitary groups. And so, oops. So I'm going to first explain what this is in the compact case, which is this is the classical result of Herman-Weyl, and then I'll explain what this conjecture is, and finally I'm going to explain how to prove it. And as you're going to see, the proof is quite simple and straightforward. So first, let's explain what the classical branching problem is, and this is the classical result of Herman-Weyl. So we write un for the compact unitary group in variables, and say pi, this is the irreducible representation of un plus 1, again compact. Now the question is, how does this pi decompose when you restrict this to un? So of course, this pi is irreducible as a representation of un plus 1. It's not going to be, most of the time, it's not going to be irreducible as a representation of un. Now the question is asking, how does this decompose? So, well, for this, let's recall that irreducible representations of un, they are parameterized by their highest weight. So the irreducible representation of un is that corresponds in one-to-one correspondence with a sequence of a decreasing sequence of integers. So a1, a2, all the way to an. These are integers, and this is the highest weight. So we said that pi is the irreducible representation of un plus 1. So pi corresponds to a1, a2, all the way to an plus 1 integers, decreasing the sequence of integers. And the sigma, say this is the irreducible representation of un, and then sigma would correspond to another sequence of decreasing sequence of integers, b1, b2, all the way to bn. So now having this setup, we could state Weyl's branching law. The result of Weyl says that, well, if we restrict this pi, which is the representation of un plus 1, if we restrict that to un, then it decomposes. And the decomposition is multiplicity free. Namely, we got a direct sum of irreducible representations of un, and each appears with multiplicity 1. And the sigma, being a representation of un, the sigma appears in this decomposition if and only if we have this very nice sandwich condition here. So the parameter b1, b2, all the way to bn is sandwiched in between the other sequence a1, a2, all the way to an. So that's a very beautiful characterization of a decomposition of the decomposition of pi when you restrict to un. So that's the classical theorem of Weyl, Herman-Weyl, and this is the original source of this branching theorem. So the book is this, the theory of groups and quantum mechanics, and this is essentially the last page of the book. It might be very small here. I'm not sure if you can read it, but you can see this. Well, the notation is different, but you can see this sandwich condition here. This is the condition appearing in that branching theorem. It's, well, I read a little bit of this book. It's in fact quite pleasant to read it. So that's the compact situation, and the question is, of course, well, we're going to ask, well, what if the unitary groups, what if they're not compact? Well, in that case, then you would have to think. So, well, the first question in the non-compact situation is that, well, now let's recall. Well, in the compact case, we could parameterize representation, irreducible representations of unitary groups by their highest weight. And there's a very nice one-to-one correspondence. Now, for non-compact unitary groups, how do we parameterize these representations? Well, there are many different parameterizations of this, but what we're going to make use of is the so-called Vogan parameterization. And let me explain that. Well, say this V, this is the formation space of dimension n, and pi, this is a irreducible representation of UV, the unitary group given by this formation space. Now, the Vogan parameterization, in fact, parameterizes this representing pi by a pair, this phi pi and eta pi, where this phi pi is an L parameter and this eta pi is a character of an abelian 2 group. So let me explain them. So let me first explain what the L parameters are. Well, here are some terminologies. So we call a character of C cross. We call its conjugate self-dual of sign +1 or sign -1. If that's of this form, z it's z over z to the m divided by the norm to the m. So it's of sign +1 if this power is even, and it's sign -1 if the power is odd. It's a parity condition here. And if this C is a character of C cross, then we put this C conjugate by conjugation on the variables. So this is C Z bar. Now, what is the L parameter for unitary grouping in n variables? This is a particularly simple case where we can make everything explicit. Now, L parameter, this is a semi-simple n-dimensional conjugate self-dual representation of sign -1 to the n of C cross. Okay, it's a very long sentence, but whatever that is, it is nothing but a direct sum of characters, a direct sum of n characters, and I write this this direct sum in this form, where. So in this first big direct sum, everything is conjugate self-dual of sign -1 to the n -1. So this part consists of characters that are of correct signature. So it's again, it's a parity condition. And this second big direct sum, it consists of characters not of the correct conjugate self-dual sign condition. And because they do not have the same, they do not have the correct conjugate self-dual parity condition, they should appear in pairs. So if this C k plus I is there, then the conjugate inverse should also be there. So that's what an L parameter is. Now, to an L parameter, we can attach a Vogan packet to that. So again, say this V is a Hermitian space of dimension n. And this phi, this is an L parameter for unitary groups in n variables, just what I have described before. It's a direct sum of characters. And say, and then first we have an L packet. This is, I denote this by big pi phi v. And this is a finite set of irreducible representations of UV. Okay, and this these L packets, in fact, give a partition of all irreducible representations of UV. But what we're going to do for the Vogan packet is that for this particular L packet, we take the disjoint union over all Hermitian spaces of dimension n. So for fixed L parameter, we take the disjoint union of all L packets when varying this Hermitian space with a fixed dimension. And that's what a Vogan packet is. Now, here's one example of a Vogan packet. Now, a Vogan packet, say, if this pi is a irreducible principal series, the principal series of unitary group p plus 1p, then the Vogan packet here now this time consists of two consists of two representations. One is, of course, this pi as a representation of this unitary group UP plus 1p, and we got a repetition here. The other element is the same representation pi, but this pi is viewed as a representation of UP p plus 1. So as representations, they are the same, but the groups, they are just abstractly isomorphic, but they are not considered as the same unitary group because they are the unitary groups of different signature. So now just from this example, you see that, well, Vogan packets here, there might be some redundancies in this Vogan packet because the same representation might appear twice as representations of different unitary groups. So now once we have these Vogan packets, we could ask for an internal parameterization in a Vogan packet. So recall that we have this L parameter like this. It's a direct sum of characters like this as before. Now we define in this ad hoc manner a centralizer, this A phi, and this is nothing but a bunch of copies of Z mod 2Z. And the number of Z mod 2Z's here is precisely the number of distinct conjugate self-dual characters of the correct sign, which is basically this part. So that's the centralizer. It's just a billion two group, and we just define it directly like this. Now the result of the Vogan parameterization is that each Vogan packet, the Vogan packet is in one-to-one. The elements in a Vogan packet, it's in one-to-one correspondence with the characters on this centralizer. In particular, they have the same cardinality. So the cardinality of this guy is 2 to the k, and of course the number of elements in the Vogan packet is again 2 to the k. So to summarize, to each L parameter phi and to each of this character on the centralizer, this phi and eta, correspond to a Hermitian space V and a representation pi as a representation of the unitary group UV. And it's important that the Hermitian space, this Hermitian space, is part of the data. So that's the internal parameterization in a Vogan packet. And there's a little subtlety here. This parameterization is not super canonical. It depends on the choice of some Whittaker datum, but I'm not going to explain that. It's quite confusing. So the Vogan packets that we're going to be dealing with are the so-called generic packets. So what is a generic packet? Generic packet is a packet that contains a generic representation. That is a generic packet. If that contains a generic representation, then the packet is said to be generic. Now, in this case, well, for generic packets, a generic packet would consist of irreducible parabolic inductions of limits of discrete series representations. So generic packets are quite easy to describe. And one remark is that tempered packets are all generic. So tempered could either mean that, well, the representation inside are all tempered, or in terms of the parameters, it means that the characters appearing in the L parameter, they are all unitary. So tempered packets are all generic. So we're going to be working with only generic packets for the local Gan-Gross-Prasad conjecture. Well, recently, Gan-Gross and Prasad, they extended their conjectures beyond the generic case. They consider some larger class of representations, but we're not going to deal with that here. we work only with the generic packets. So now I would like to talk about the representations. So now we consider two Hermitian spaces, W and V, and they are Hermitian spaces of dimension n and dimension n+1. One is contained in the other one. So say pi is the irreducible representation of UV and sigma is the irreducible representation of UW. So here I should make a note that by a representation, I really mean the smooth Fréchet representation of moderate growth, or this is the same thing as the canonical Castleman-Wally globalization of an admissible GK module. So this is quite a technical point, but I should point out that the theorem or the Gan-Gross-Prasad conjecture will hold only for these kind of representations. If you work in the category of GK modules, the statement would not hold. So we have representations pi, which is a representation of unitary group in n+1 variables. This is UV, and we have representation sigma. This is a irreducible representation of UN, a unitary group in n variables. So now we define this multiplicity. This is essentially just the detects whether the sigma appears in the decomposition of pi when restricted to UW. Well, for technical reasons, it's better to formulate this multiplicity in the form of this invariant linear forms, and that's for technical reasons here, and also for the global applications to the global Gan-Gross-Prasad conjectures. This is the most suitable formulation of this multiplicity.
Sorry, so you say that if I just did the GK modules, this version would not work?
Yeah, right. If you just work with GK modules, then that multiplicity one would not hold. For example, if you work with GK modules and if you consider generic representations, then the Whittaker model is not unique.
Yeah, the Whittaker one is bad, but does this one also have that feature?
This one, I'm not sure that in the codimension one case, I'm not sure.
Oh, I see. You're worried about Bessel models and so on as well.
Yes.
I see. Okay, thank you.
So that's the multiplicity, that multiplicity that we define. And well, the first thing here is that this multiplicity is at most one, and this corresponds to the conclusion in the compact case that when you take the restriction of pi to UN in the compact case, it's a multiplicity-free direct sum. And here in the non-compact case, we still have this multiplicity one. And this is the result of Sun Mingyu and the Zhu Chengbo maybe 9 years ago or 10 years ago. And this is where this theorem is coming from, and it's theorem B in that paper, and it says that this multiplicity is at most one. Now, well, we know that the multiplicity is one. So of course the question is, when is it one and when is it zero? So you just got two choices, and you definitely would like to figure that out. And so when is this multiplicity non-zero? Namely, it's one. And this is the content of the local Gan-Gross-Prasad conjecture. And this is their book. It's this is the book published by Asterisk. The title of the paper is this: symplectic local root numbers and so on. It's a long title. And the conjecture is stated here. This is conjecture 17.3. That's what the conjecture is. The local Gan-Gross-Prasad conjecture. So the notation is a bit different from ours, but I want to say that the theorem that I'm going to state will confirm this conjecture for unitary groups. So that's the conjecture. So now let me state the result. So the setup is as follows: we have two we have two L parameters. One is phi n plus 1, and the other one is phi n. They are generic L parameters for unitary group in n variables, and the other one for unitary group in n variables. So this is for n plus 1 variables. This is for n variables. And we have the corresponding Vogan packets. This and that. They are the Vogan packets. And we have the corresponding centralizers. This A n plus 1, and this is our A phi n. So now here's the theorem. This theorem consists of two parts. The first one is the so-called multiplicity one in a Vogan packet. And what it states is that, basically, it says that inside a Vogan packet, there exists a unique element of multiplicity 1. And everything else is of multiplicity 0. But one needs to be careful, because we're looking at the representations only here. And we have said that inside a Vogan packet, there might be some redundancies. Like the representations might repeat itself twice. So to make this absolutely correct, we need to take just half of the Vogan packets. And this is what we do. We take all the disjoint union of all these L packets, but only when there's two Hermitian spaces, this W and V, one contained in the other, but we actually fix the sign of the quotient. We fix the sign of this quotient V and W. So we fix that the sign is -1 to the n. So the sign could, for arbitrary V and W, the sign could be either +1 or -1. But once we have fixed this sign, then we are essentially taking only half of the Vogan packet. So this is merely a technical thing. You should really understand this part of the statement as there exists a unique element inside the Vogan packet with multiplicity 1. Okay, that's the first part. Now, because this is a unique element, so of course you want to specify that, and the second part of the theorem actually specifies this. So it specifies inside this Vogan packet which representation is of multiplicity 1. We know that there is a unique one, and the second part specifies which one. And the specification is using the internal parameterization inside a Vogan packet. And this side, this epsilon thing, these are the so-called local root numbers. And they can be made very explicit in this case. They are just plus minus ones. These are just plus minus ones. And in the case, because we're in the Archimedean situation, so these local root numbers are quite easy to compute. So this is the theorem. Well, the first part of the theorem states that inside a Vogan packet, there exists a unique element, which is of multiplicity 1. And the second part states which one is of multiplicity 1. And the specification is in terms of the long-length Vogan parameterization and in terms of the local root numbers. So let me say a little bit about these local root numbers. These local root numbers, first, it depends on the choice of the additive character, and this is some mirror image of the fact that the internal parameterization of a Vogan packet actually depends on the choice of a Weyl model. And well, in this case, in the Archimedean situation, they can be made very explicit. So because this phi n it's just a direct sum of characters, so the local Vogan, the local root numbers, it's the product of the local root numbers of the characters. And well, for the local root numbers of the characters, it's very simple to compute. And another paper in the same book, again by Gan-Gross-Prasad, they made this really explicit. As you can see that here, it's essentially when you choose everything correctly, it's essentially just a sign character. Okay. This is not anything super fancy as in the case of p-adic. As for p-adic groups, these local root numbers might be very hard to compute, but in the Archimedean case, everything can be made super explicit. Okay, now the Bessel models, there's a similar version of the restriction problem for the Gan-Gross-Prasad conjecture for unitary groups of this form. So previously we were considering unitary groups of so let's say un and un, the UN and UN plus 1. But you could also consider these so-called Bessel models. They are on the represented on this represented branching problem for two unitary groups where their size differ by an odd number. So it's UN and UN plus 2T plus 1. And this involves some unipotent subgroup and also a generic character. We also prove the Gan-Gross-Prasad conjecture in this setting, and the proof is actually by reducing it back to this codimension 1 case. So I'm not going to explain too much on this, but I will mainly explain the proof in the codimension 1 case. So let me summarize something about the previous work. So mainly 2 pieces. The first one is by He Hongyu, and he proved the Gan-Gross-Prasad conjecture for in the case of in the case of discrete series representations. And that's the reference. And the other one is by Raphael, and he proved the so-called multiplicity one in a Vogan packet for tempered packets. So recall that the theorem consists of 2 parts. The first one states that in a Vogan packet there exists a unique member with multiplicity 1, and he basically proved that part for tempered packets. And this is the paper. It's just published again by Asterisk, and this paper I should say I am pretty lucky to have witnessed the birth of this paper. A couple of years ago, when he and myself, we were both at IAS doing postdocs, and he was writing this paper, and he was working extremely hard on this, and every time he made some progress, he lectured to me. And well, I was just out of the graduate school, and I was not able to understand much, but I still pretend that, okay, yeah, that makes sense. Yes, that makes sense. Well, I thought that I didn't understand much from that. Well, he was just lecturing on a lot of harmonic analysis on Blackboard, and I thought that I didn't understand much. But later on when I turned back to this paper and to my memory, I really found that I learned a lot from him. And in fact, I like this paper very much. I like this paper very much. Well, but one drawback of this is that you see the keywords, a local trace formula. Well, that says everything. If you see something about the trace formula, usually it means that it's technically very hard and it's going to be very long. And in fact, it is. This paper, originally the first version is like 250 pages, and the final published version is more than 300 pages. And it's really a huge amount of work in order to do that. And in fact, if you want to prove the full local Gross-Prasad conjecture for the full conjecture, namely you want to specify which elements in a Vogan packet equals 1 with multiplicity 1, then you need another version of this. So if you were to follow this route, then you need another version of so it's a twisted local trace formula for this, and you need to write again hundreds of pages, but it's certainly doable. It's just pretty hard. But I should point out that this method is very powerful, that it works both for the Archimedean case and the p-adic case. In fact, even though the title of the paper says that the Archimedean case, this is really a uniform treatment of the local Gan-Gross-Prasad conjecture for both Archimedean case and the p-adic case. Okay, while my proof works only for the Archimedean case and it works only for the unitary groups. You're going to see why. So even though this paper is very long, I would recommend anyone interested in the subject to read it, at least to read part of it. I just like it so much. So so for the rest of the talk, I'm going to explain my proof. The proof consists of two steps. So the first one is to prove the temporal case, and the second one is to prove to prove a reduction to the temporal case, and they correspond to two papers. And the first one is so both of them, and the first one is the temporal case, and the second one is the reduction to the temporal case. Especially for this first paper, this paper is very short and easy to read. This is only like 15 pages, and it makes uses of data correspondence instead of the choice formula, and that makes the proof very, very simple. And you can find these two papers on my website. So before I get into the proof, let me make some remarks. So the first one is that the proof is based on data lifts and something about the Schwarz analysis. It is independent of the choice formula approach. It has nothing to do with the choice formula. And the second remark is that it is also independent of the work of He Hongyu. Well, it is quite tempting to say that, okay, he has already proved the discrete series to prove the theorem for discrete series representation. Maybe we should try to reduce to that. And that was my initial attempt. But it turns out that it is not as simple as you do it directly. So from the final argument has nothing to do again with his work, and it does not reduce to the case of discrete series representations. And the next thing I want to say is that the argument makes very explicit use of the structure of real unitary groups. It does not apply to p-adic unitary groups or to orthogonal groups. So this is a technique specifically tailored for real unitary groups. And I'm still trying to figure out if anything can be done in the case of orthogonal groups. But so far as the method that I'm going to present here, it cannot be adapted to the orthogonal group case without any serious modification. And the last remark I want to say is that we need to treat the temporal case first, because there's a technical issue with data lifts. It's really a technical thing. Well, if we could resolve this technical problem with data lifts, then we should be able to get the so-called Fourier-Jacobi case. But I'm still working on that. So now I'm going to explain the proof, and the proof, a large part is by theta lifts. So let me explain what this theta lifts is. Well, this is a long story, of course, if you want to build everything from scratch. But what you need to know is that this is a systematic and explicit way to construct the irreducible representations of unitary group from another one. So most of the time from un to un plus 1. So you have a representation for unitary groups in n variables, and you want to construct another representation for unitary groups in n plus 1 variables. And this is a very good tool. So one nice part of this is that the relation between the Langlands-Vogan parametrization of pi prime and pi, so they can be made very explicit. So the construction of the representation is explicit, and the Langlands-Vogan parametrization is also explicit. And this is the work of many people, and in the case of real unitary groups, it's finally worked out by Annegret Pohl. Now, the sad news is that, well, not all representations of un plus 1 can be constructed from un. If we were able to do that, well, of course, we're going to be good, because we got an explicit construction of all representations, and we can make use of it to reduce the size of the unitary group. That would be wonderful if we had that. But apparently life is not so easy, and we do not have this. So here comes the key observation. So we're not able to construct all representations, but what can we construct using theta lifts? So say pi, this is a irreducible representation of some un plus 1, compact or not. It might or might not be compact. Now, assume that this pi corresponds to this Longland's Vogan parameterization, this phi pi and eta pi. Now, the first observation is that we do not construct pi. We do not construct pi, but we construct pi up to a twist by the determinant. So pi up to a twist of the determinant can be constructed from a theta lift from some un if and only if this the parameter of that contains some conjugate self-dual character of the correct sign. So this is a much relaxed condition, that you want to actually construct pi, but we actually construct pi up to a determinant. And the condition, the necessary and the sufficient condition here are imposed on the L parameter, namely, as long as this L parameter contains some conjugate self-dual character of the correct sign, then we can do it. So if the parameter contains the conjugate self-dual character of the correct sign as this, then this whole packet, not just this representation, but this whole packet can be constructed by theta lifts from the unitary group in n variables. Again, of course, up to the twist of the determinants. So we actually need the composition of two theta lifts. So we have this pi. We have this pi, which is here. This is the unitary group in n plus 1 variables. And if this phi pi contains at least two conjugate self-dual characters of the correct sign, which is here, then we are able to find a unitary group in n variables, which is here, and the unitary group in n minus 1 variables, which is here. And what we do is that we could find a representation, say pi 0. We take a theta lift and make a determinant twist, and then we make another theta lift and make a determinant twist. And then we got this pi. That is the construction. So each step, we do not construct the representation directly, but instead we construct the representation up to a twist by the determinant. So that's the construction from theta lifts that we're going to make use of. So why is this? Why can we just construct representations just by up to a twist? Well, the reason for this is that this multiplicity has nothing to do with this twist. If we twist one by the determinant and twist one by the determinant inverse, then we get the same multiplicity. Well, I feel quite bad that it took me hours just to realize this simple fact. And when I was first realized that something like this might be true, I could not even believe it. And I say, how come that this is true? And I was walking upstairs and downstairs in my house for like an hour, and then I realized that, okay, come on, this is completely trivial. The reason for this is that the determinant of un plus 1, if you restrict to un, is still the determinant. That's completely trivial. Well, it's just this. I feel pretty bad about this. Indeed, it's a very tiny little thing, but it makes life much easier. So this is the reason why we could just construct the representations up to a twist by determinant, not just the representation itself. Okay, now the main tool in using theta correspondence, if you have ever played with theta correspondence, you will know that the main tool here is the so-called seesaw diagram. So what's that? Now suppose this pi, the L parameter of pi contains a conjugate self-dual character, the conjugate self-dual characters of sign minus 1 to the n. So a conjugate self-dual characters of the correct sign, and the L parameter phi sigma, and b conjugate self-dual characters of the correct sign. And let's assume that this a is at least 2. So we need this the a to be at least 2 in order to play with the theta lifts. So the theta lift argument tells you that, well, when this pi the L parameter contains A conjugate self-dual characters and A bigger or equal to 2, then we know that this pi can be constructed via the two-step data lifts. So you go from pi 0 to pi prime and then pi. Now, what the Seesaw argument actually tells you is that we could find this pi 0, which is the one that I have set, and another sigma 0, such that they have the same multiplicity. And what is this sigma 0? The sigma 0 is another irreducible representation of some unitary group un, and this pi 0 is a irreducible representation of some unitary group un minus 1. So actually, we're reducing the size of the unitary group here. But that's not the most important part. The most important part is that we're not merely reducing the size of the unitary group, but instead, we're reducing the number of conjugate self-dual characters of the correct sign in the L parameter. Namely, this phi pi 0 contains A minus 2 conjugate self-dual the characters of the correct sign, and this phi 0, the phi sigma 0 contains B conjugate self-dual characters of the correct sign. Namely, when you do the data lift from the small group to the big group, you do it twice. You are reducing the size. You are reducing the number of conjugate self-dual characters by 2, and this is very, very important. This is perhaps one of the most important observations in this argument. So the Seesaw arguments can be summarized as follows. You have the Gan-Gross-Prasad for un plus 1 cross un, and you do one Seesaw argument. You end up with the Gross-Prasad for un and un, and you do another one. You end up with the Gross-Prasad for un and un minus 1. So that's the two-step Seesaw argument. And if you have ever played with the data lifts, then that's the diagram, the Seesaw diagram that I made use of.
So sorry, is that the Seesaw? Sorry, is that the
Yes?
Seesaw for the upper arrow or the lower arrow?
This one is for, let me see. This one is for the upper one, and for the lower one, you replace everything on this side. This is going to be un, and this is going to be n minus 1.
Okay, thank you.
So now let me give you the proof of the temper case. This is a trick. So recall that in our setup, we have pi and we have sigma. They are in this Vogan packet, and the sigma in this Vogan packet. And this pi correspond to eta pi and sigma correspond to eta pi. Eta sigma for the Langlands Vogan parameterization. So that's our setup. And let's assume that this phi n plus 1 contains A conjugate self-dual characters of the correct sign, and the phi n contains B conjugate self-dual characters of the correct sign. Now, the major trick of the argument is that we prove the theorem by doing an induction on A plus B. That's the main trick. We prove the theorem by doing an induction on A plus B, not the size of the unitary group. And the observation is that this A plus B has to be odd. The reason being that this A has to be of the same parity with n plus 1, and this B has to be of the same parity with n. So A plus B has to be of the same parity with 2n plus 1, so it has to be odd. So the base case, well, it's an odd positive non-negative integer. So the base case is A plus B equals 1. So one of them is 1, the other one is 0. Now, in this case, you work a little bit. You see that this pi and sigma are irreducible principal series representations. And these two characters are both trivial. And the local root number equals 1 if you choose everything correctly. And the multiplicity is also 1 because they are just the irreducible principal series representations. So the theorem holds for pi and sigma. So this is our base case. It's quite straightforward. Now we assume that A plus B is bigger than 1, and because that's odd, so it has to be at least 3. So we should have either A bigger or equal to 2, or B bigger or equal to 2. Now let's assume that A at least 2 first. Now in this case, we know that because A is at least 2, we know that we can do that Seesaw argument. So we got this pi and sigma, and we produce two other representations, sigma 0 and pi 0, and they are irreducible representations of unitary groups of smaller size. But more importantly, this pi 0 contains a minus 2 conjugate self-dual characters of the correct sign. And this sigma contains b conjugate self-dual characters of the correct sign. So we are actually we have actually reduced the number a plus b to a plus b minus 2. So we can use induction, and the theorem would hold for sigma 0 and pi 0 by the induction hypothesis, and therefore the theorem should hold for pi and sigma because they have the same multiplicity. Okay, that's the case A at least 2. Now, to treat the case B at least 2, we need another tool called induction and multiplicity, and it can be briefly described as follows. So suppose we have a chain of Hermitian spaces, so WV and say W plus, where this W plus is this W the direct sum with the two-dimensional split Hermitian space, and this P, this is the parabolic subgroup of this UW plus, and the Levy part is the C cross and the UV. So this unitary group attached to this W essentially appears as the Levy component of this parabolic subgroup. And now we form a parabolic induction from P to this bigger unitary group, and on this unitary group, it's just the sigma, and on this C part, it's the absolute value to the IT, where T is a real number. And for a generic T, for you pick a random T, then this should not change the multiplicity. And now, well, for sigma plus, we know how to write down the L parameter, the Langlands Vogan parameter, the parameter for the sigma plus. It's quite simple. You just take the direct sum with two other characters. That's quite simple. And because we are just adding adding non-conjugate self-dual characters here, this will not change the centralizer nor this eta. So now we can handle the case B at least 2. So assume that B at least 2. Now we take a generic real number and consider this induced representation, the sigma plus. Just consider this. So now this becomes the representation on the level of the big group. So therefore, by the previous case, we know that the theorem should hold for sigma plus and pi. Now the theorem should hold for pi and sigma because they have the same multiplicity. And that's it. And this completes the proof in the temper case. So it's a quite straightforward argument. So basically, we are making use of the theta lifts and this kind of induction techniques to simplify the L packet. I really would like to formulate the proof as simplifying the L packets. So that's the temper case. Now the generic case. So I would not have enough time to explain the full proof of the generic case. If I were to talk another hour, then perhaps I can do it. But so let me briefly explain how you could do the generic case. So say now here this pi and sigma they lie in a generic packet. So they are of this form. So here this pi 0 and sigma 0, they have different meanings from the previous ones, and these are characters. So by cross I mean the parabolic induction. So this pi and sigma are of this form. So they are irreducible parabolically induced representations. So this pi 0 and sigma 0, they are limits of discrete series representations. And these things are just characters, not necessarily unitary. If they were unitary, then we're in the temper case. But here in the generic case, they might or might not be unitary. So because they are irreducible, the irreducible parabolic inductions, we are really studying the restriction problem of the induced representations. So for this, we have a big toolbox. And this is the toolbox. So we're gonna make use of the so-called Schwarz induction due to the Ducreux and and a bunch of other Schwarz analysis techniques like Borel's lemma, or the recent technique on a new homology theory, group homology theory called Schwarz homology. This is by Chen Yang and Sun Mingnu. So that's the toolbox. So the idea of the proof is that, well, previously we see that these might or might not be unitary characters, and if they were unitary characters, then we are good. So the idea is that we put these potentially non-unitary characters into a suitable order, and we replace them one by one by the unitary ones, so that the multiplicity is going to be preserved in this process. So basically, we are doing like inductions and restrictions and inductions and restrictions a couple of times during this process. So the upshot is that we could find a bunch of generic purely imaginary numbers, S1 prime, SA prime, T1 prime, TB prime. They are purely imaginary numbers, and we could form the representations pi a and sigma b so that they are of this form. Again, parabolic inductions. Well, it's the same form as this pi and sigma, except that the potentially non-unitary characters are replaced by these unitary ones. And the key property is that in this process, the multiplicity is not changed. And because of this, the representations, this pi a and sigma b, they are unitary because this is limit of discrete series, and these are generic, these are unitary characters, so they are tempered. So the theorem holds for this pi a and sigma b, and because they have the same multiplicity, so the theorem would hold for pi and sigma. And that's going to be the proof for, or the idea of the proof in the generic case. So that's the end, and thank you very much. Thank you.
All right, let us unmute ourselves and thanks Han, phase 1 for talk. Questions?
So I'm used to using Seesaw for global periods. So what exact properties of the theta correspondence are you using to pull the, say, the multiplicities are equal?
Okay, that's a very good point. So let me see where we are. So we are here. We are here. So basically, like you take. So in fact, what I'm using is not a purely representation theoretic thing, because that's, I said that there is a problem with data lifts that prevents me from doing this. But what I have used here is that instead of looking at the multiplicity here, I'm looking at the integration of matrix coefficients. So for integration of matrix coefficients, the Seesaw diagram essentially reduces to a change of the change of order of integration. So that's like the concrete version of this Seesaw. The abstract version actually is quite similar, but I need something. I will need something like this. Can I annotate? I don't think I can annotate. Could you give me the host?
You need to be host, or?
And I guess I need to be a co-host in order to annotate that.
Let me try to make it host.
So in what you just said, you would be using the fact that if it's abstractly distinguished, it is in fact the integral of matrix coefficients is not zero.
Yes.
I see.
Yes. So the abstract thing has a problem. Well, I don't think I can annotate, but anyway, the problem with data lifts that the problem with data lifts that I have here is that there's a problem with there's a distinction between the so-called full data lifts and its maximum simple quotient. So for theta lifts, usually it's defined as a two-step process. The full data lifts is defined to be the, say, you want to describe the data lifts for pi, then the full data lift is defined to be the pi isotypic component of the Weyl representation. And the actual data lift is the unique irreducible quotient of this. But what I really need here, it would be that for generic, so for representations lying in a generic packet, we need that full data lift to be irreducible. And this is true in the PLA case, but in the Archimedean case, it needs to, it's missing in the literature and it needs to be worked out. So far,
something goes wrong.
Seems we have lost Tom.
all right, there might be a problem with connection or something.
Right.
Right, it's good now.
Let me still share this. I don't hear anything. Do I miss anything? Yes, no.
No, we're waiting for you.
I don't hear anything. Am I in a good shape or no?
I think you hear us.
Okay.
Yeah. So maybe there are more questions.
Yeah. So can you give us a basic idea what's exactly going on with the local GGP and then in the both unitary orthogonal case? In non-commutative case, it's completely done or still?
Well, in the PID case, it's completely done. For PID groups, it's the work of Waspujet and Raphael. They basically completely proved the PID case. And for real groups, unitary groups, it's okay. Orthogonal groups, it's there's a student of Zhang Lihua who recently set up the local trace model, maybe prove the multiplicity one in a tempered packet for orthogonal groups. I think it might be his thesis, but I forgot the name of the student. And basically that's it.
So so unitary case, that's your work, right?
Yes.
For orthogonal case, it's not a
Well, the orthogonal groups, it's going to be different from this one because for orthogonal groups, you're not able to construct representations as simple as this one.
Right.
Because well, basically, for unitary groups, L parameters are sum of characters, and this is good. But for orthogonal groups, say SO2n plus 1, for discrete series, then the L parameter will be the direct sum of two-dimensional representations. Then you are not able to construct these representations directly using theta correspondence. So basically, the theta correspondence likes characters, and other than that, it's somewhat beyond the scope of theta libs.
The orthogonal part is also done, right?
Sorry?
Discrete, sorry, the discrete series. Orthogonal group.
No. Even for discrete series, it's not known. Essentially proved I think he proved the unitary group for discrete series codimension 1, and he also made a conjecture for like some kind of constructing technique for orthogonal groups for other orthogonal groups, and that's it.
So this slide seems to say that you reduce to the Fourier-Jacobi case, or like that's a reduction step in your argument, but you also said that case doesn't actually work out. Can you explain that?
Well, what this slide actually says is that, well, the distinction by integration of matrix coefficients is equivalent to that local root number condition in the Fourier-Jacobi case. So there are two kinds of distinctions. One is the abstract distinction problem using just the representations, and the other one is the integration of matrix coefficients. And integration of matrix coefficients is stronger. And what this argument says is that the integration of matrix coefficients non-vanishing is equivalent to the local root number condition.
But what goes wrong in the Fourier-Jacobi case?
Nothing goes wrong there if you use the integration of matrix coefficients. It's just that in the Fourier-Jacobi case, it is not known that the abstract the distinction as abstract representations is the same as integration of matrix coefficients.
I see, but it's supposed to be true?
Of course.
I don't think there's any real problem with the argument. I would have thought, for example, the argument for that in my book with Yanis should be adaptable.
Yes, it is. It's just that no one has done it.
I see. Okay.
It's not a problem. I'm not saying it's a problem. It's
okay.
Work. Or maybe it's just labor. It's not a problem.
So if there is no more question, let us thanks Hanshu again.